As we all know that there are two main parts of calculus. One is the derivatives, which we have discussed in the previous lectures, and in that we came to know that how to find the derivatives of a function and how to use them to solve the wide range of problems. They can be used to measure the instantaneous change, while the second part is integrals, which measures the cumulative amount. Many problems requires that we recover function from its known derivatives, which are basically the rate of change. For example, the laws of physics tells us the acceleration of an object falling from an initial height, and we can use this to compute its velocity and its height at any time. More generally, starting with a function small f, we want to find a function capital F whose derivative is f. So if such a function capital F exists, it is called an antiderivative of the function. Now, if we want to find an antiderivative of 2x, then the function capital F equals to x square is not the only function whose derivative is 2x. The function x square plus 1 has the same derivative, so does x square plus c for any constant c. So, corollary of the mean value theorem says that any two antiderivatives of a function differ by constant. So, functions x square plus c, where c is a constant, form all the antiderivatives of the function 2x, and more generally, there is a specific result too, uh, which is basically if capital F is an antiderivative of f on an interval I, then the most general antiderivative of a function on the interval I is capital F of x plus c, where capital F of x is an antiderivative of the function small f and c is an arbitrary constant. So we can say that the process of recovering a function capital F of x from its derivative f of x is called an anti-differentiation, and we use capital letters such as capital F to represent an antiderivative of a function. Here is a function in which we have to find an antiderivative of this function. The antiderivative of this function is antiderivative of 1 by x is ln x, and antiderivative of 2 e raised to the power 2x is e raised to the power 2x. So we can say that if we'll differentiate this expression, we'll get this function. Okay, now we can say that the most general antiderivative of a function on the interval is basically a family of function capital F of x plus c whose graphs are vertical translations of one another. We can select a particular antiderivative from this family by assigning a specific value to c. So here is an example showing how such an assignment might be made. So we can see this example, that find an antiderivative of a function 3x squared that satisfies the condition f of 1 equals to minus 1. This condition says that at x equals to 1, the value of capital F is minus 1. So the antiderivative of function 3x square is x cube plus c. Substituting the value of x equals to 1 and value of f equals to minus 1 in the expression, we get c equals to minus 2. So the function, uh, so the antiderivative of this function 3x square is x cube minus 2. Now here is another function whose antiderivative we have to find. The antiderivative of this general function is 6 under the radical x minus 1 by 2 cos of 2x plus c. So by working backward from assorted differentiation rules, we can derive formulas and rules for antiderivatives. So the rules of antiderivatives or indefinite integrals are here, that if f of x is 1, its antiderivative is x plus c. If the function is x raised to the power n, its antiderivative is x raised to the power n by n plus 1 plus c. If function is 1 by x, its antiderivative is ln x. If function is e raised to the power x, the antiderivative is e raised to the power x plus c. Function is sin x, its antiderivative is minus cos x plus c, and so on. And here are the rules for the antiderivatives. The constant factor rule, this says that if a constant is multiplying with the function, then you can take out constant and integrate the function and you get the answer. The negative rule, if a negative sign is multiplying with a function, then that negative sign is also multiplied with the antiderivative of the function. The sum and difference rule, if two functions are adding or they are being subtracted, then as integral is a linear operator, it is applied term by term, so you can get the answer. And these rules are applied here, that integral or taking integral of this function is integral of the first function plus integral of the second function. So integral of first function is e raised to the power 3x by 3 and integral of second function is ln x. Now let's discuss the topic of initial value problem and differential equations. Well, antiderivatives play several important roles in mathematics and its applications. Methods and techniques for finding them are a major part of calculus. And finding an antiderivative for a function f of x is the same problem as finding a function y of x that satisfies the equation dy by dx equals to f of x. This is basically a differential equation because an equation involving derivative is known as a differential equation. So to solve it, we need a function y of x that satisfies the equation. This function is found by taking the antiderivative of the function, and we can fix the arbitrary constant arising in the anti-differentiation process by specifying an initial condition y of x naught equals to y naught. This condition means the function y of x has the value y naught when the value of x is x naught. So the combination of a differential equation and an initial condition is called an initial value problem, and most journal antiderivative f of x plus c of the function f of x gives the journal solution of the differential equation. The journal solution gives all the solutions of the equation, and we can solve the differential equation by finding its journal solution. Uh, we then can solve the initial value problem by finding the particular solution that satisfies the initial condition y of x naught equals to y naught. As we have seen that the derivative of a position function of an object gives its velocity, and the derivative of its velocity function gives its acceleration. If we know an object's acceleration, then by finding an antiderivative we can recover the velocity, and from an antiderivative of the velocity we can recover its position function. So uh, here is an example in which we are trying to find out the position function. Example is a hot air balloon ascending at a rate of 12 feet per second is at a height of 80 feet above the ground when a package is being dropped. How long does it take the package to reach the ground? Now, v of t denotes the velocity of the package at time t, and let s of t denotes its height above the ground. So the acceleration of gravity near the surface of the earth is 32 feet per second square. So what will be our differential equation? Our differential equation will be dv by dt equals to minus 32 because gravity is acting downward. What is the initial condition? Initial condition is at time 0 the velocity is 12 as balloon is initially rising upwards. Okay, so we integrating this expression, integral of dv equals to minus 32 minus integral of 32 dt, we get v equals to minus 32 t plus c. Now substituting the value of t equals to 0 and velocity value 12 in the expression, we get the value of c, the constant of integration, t equals to 12. So the initial value problem is now v equals to minus 32t plus 12. Since the velocity is the derivative of height and height of the package is 80 feet, at the time t equals to 0, 1, it is dropped. So the equation becomes ds by dt equals to minus 32t plus 12. Solving this differential equation, integral of dv equals to minus 32t plus 12 into dt. So we get s is equals to minus 16t square plus 12t plus c. Substituting the value of t equals to 0 and s equals to 80 in this expression, we get c equals to 80. So the equation becomes s is equals to minus 16t square plus 12t plus 80. Now to find how long it takes the package to reach the ground, we set s equals to 0. Setting s equals to 0, we get two different values of time. One is t equals to minus 1.89 and the other one is 2.64. So the package hits the ground at about 2.64 seconds after it's being dropped from the balloon. Now comes the indefinite integrals. As we all know that there are two kinds of integrals. One are known as the definite integrals, other one are known as the indefinite integrals. So antiderivatives or indefinite integrals both are the same things. So the indefinite integrals or the general antiderivatives integral f of x dx of a function f of x stands for all possible antiderivatives of a function which are defined on an interval. We can solve them by this, and f of x is an arbitrary antiderivative of the function, and in the above given expression integral f of x dx is basically the function. It is called the integrand. D of x is the differential and c is the constant, and it is known as the constant of integration. Now comes the exercise questions. I have solved few questions for you people, and after listening to this theory you can solve these questions and check your concept.